Okay, let us start our discussion today. Welcome everybody. We'll be talking about constituents and the thermodynamics of the interstellar medium. This is the second lecture on the interstellar medium. And today's lecture, as we have already said, focuses on a very vast topic. And it's a topic which has been pursued by people over last 70 years. And let me tell you that obviously in one lecture we'll not be able to cover a lot of it. We'll just be covering the basics. If you want to know more, you are interested about it and want to work on it in future, you must read this book. It's a very, very nice book on the physics of the interstellar intergalactic medium. And I have also listed three very key papers in this particular topic, and some of the results of these papers we'll be using today. So yeah, so this is the first paper that I will be using, 1965, then 1969, and this is more recent, like 1977, and there is one more paper of which I will use the results in 2003. So I will request you to either go through this lecture video for this particular topic, or go through this book and don't try to go through anything else, because as I said, it's a very vast topic and I have picked up only the important bit of information for you. Okay, so what is the interstellar medium? Let me remind you, it is the medium in between the stars. And last time we have discussed what are the constituents of the interstellar medium a little bit. We said that it has the mostly hydrogen gas, it has ionized gases also, and it has dust and other things. So here we get a more detailed view of the constituents of the interstellar medium. So what I have done here is I have written the components. I'll go by them one by one. And I have the volume fractions, and I have the temperature and the density of these different parts. The temperature is given in units of Kelvin. The density is number density, so it is number per centimeter cube. So when I write this caps, it is means to the power, so which means that this is like the temperature is very high, 10 to the 6. So the first type of the medium is we call the hot ionized medium. So this is ionized, and it may contain other than hydrogen gas. It is there in almost half of the interstellar medium of a galaxy. It's very hot, and as you can expect, because it's very hot, the density is quite low. Next comes the ionized hydrogen. You can look at the numbers. Then I say warm ionized hydrogen, which is the temperature is almost similar. Then two medium which are like neutral. Instead of being ionized, now we are talking about the neutral medium, and these are mostly neutral hydrogen gas. The warm neutral medium still is extended over 10 to 20% of the ISM, but the cold neutral medium is only 1 to 5%. So you can see that they lies in the pockets of the interstellar medium. The temperature here is relatively larger. Here it is quite small, so it can go up to 1,000 or few thousands. I've just given some representative number here. And you can see as we go down the list, the density increases because the temperature decreases. And then I have the molecular hydrogen. I can have other molecular gas also, like carbon monoxide, etc. This contains even smaller part of the galaxy. The temperature is even smaller and the density is even larger. So these are eventually the clouds from which the stars will form. Then apart from this, I have also cosmic rays, which are created in supernova explosions. I have heavy shocks of the supernova explosions. I have dust. I have a very particular type of molecules called polycyclic aromatic hydrocarbon. And these are particularly important when you for the heating and cooling of the interstellar medium, but will not go into that. I have just kept the pH over here so that if you are interested, you can look into it. Then I have interstellar magnetic fields and other things. All of these takes parts in the dynamics and the thermodynamics of the interstellar medium. But again, as I said, that will not go into very detail. I also don't expect you to remember all these numbers very carefully unless you are doing a project in this particular topic. But as you can see, the volume fraction decreases as you go down. The temperature also decreases as you go down. The density, though, increases as you go down. And if you can, because you know the number density and the temperature, and all this may follow the ideal gas law, so you can use the ideal gas equation to calculate the pressure for each of these components. And surprisingly, we'll see the pressure is almost same for all the components. And that brings us to the idea of pressure equilibrium in an interstellar medium. So let us see a very cartoon picture of what is happening in an interstellar cloud. So what do I mean by cloud? I mean that maybe there is a little over density, so it looks like looks like the clouds in our atmosphere. So it's like such an interstellar cloud. It may be made up of it may be made up of atomic hydrogen. It may be made up of molecules. It can be a giant molecular cloud, which is the birthplace of stars. So it can be any such cloud. And what are the things which is happening here? This cloud being heated also from outside, because say this cloud is bombarded by cosmic rays from outside, or the shock of a supernova. There is a supernova which explodes here, and that the energy from that comes into the cloud. So these will heat up the medium inside the cloud. There will be cooling of the cloud. We will talk about how that happens. So when what I mean by cooling is some energy of the cloud is getting radiated out. So this blue lines, you can imagine, is showing the cooling of the cloud. Then there is pressure of the cloud which is being exerted on the boundary of the cloud with the otherwise outside the medium. And there can be also pressure which is coming from the outside onto the cloud. Just like if you imagine a balloon, there is a pressure from inside and there is a pressure from outside. In case of the balloon, the pressure from inside is more than the pressure from outside. That's why the balloon wants to expand, but there is surface tension of the balloon which holds it together. Now it turns out, as we have just seen, that all these different phases in the interstellar medium have the same pressure. It turns out that the pressure in this case, which is from the outside, is almost the pressure which is from the inside. And that's the reason these clouds, which are, though the overdense structures, they stay as it is. You may ask the question, how come this has more density but less pressure, where this area has less density but more pressure? Well, remember that this has less density, but according to the previous table where you have less density, I also have more temperature. And the pressure depends both on temperature and density. So that's how at the boundary of the cloud, the pressure balances, the inside and outside pressure balance, and that holds the cloud together. I can also have gravity, which is just because you have more density here, it will try to contract. And it turns out that gravity is not a major player in this game. So you can forget about the gravity, which is the gravity of the cloud. So it's called the self-gravity, while you try to write down these equations. So what we are interested to see next is the question that what holds this cloud together? So is it really that, okay, so you have more pressure out, more same pressure from outside as that in inside. So that's an equilibrium. And again, just like the last time we asked the same question, is that equilibrium a stable equilibrium or it's an unstable equilibrium? So how do you do that? So well, what all you do is you write down all the fluid equations. And that's what George Field did. And this is the oldest paper that I was talking about. And if you look at these three equations, they're nothing but the three fluid equations which you have learned many times. So this is written as a total derivative. This is nothing like del rho del t plus v dot grad rho. And if you look at this equation carefully, This is nothing but the continuity equation for the fluid. The next equation is the Euler equation. And in this case, you have not included any gravity, so the gravity term is absent. And I have the pressure term, which they have written in the left-hand side. This equation is nothing but the energy equation. It may be written in a little different form than you have seen, but it essentially is the energy equation. Here they have used the fact that they're dealing with an ideal gas, and they have used the ideal gas equation of state from which this gamma comes. So P V to the power gamma, or P rho to the power gamma, is a constant in case of ideal gas, and that is this gamma which is sitting over here. Sorry, I'm sorry. It's I meant isothermal equation of state. So that is the gamma is sitting over here. So I have these two terms. So this term gives you net cooling. So this is an energy equation, and as we said in the last figure, so the energy balance in this will depend on many things, and one will be the energy input from various sources, maybe outside, maybe inside, which you call heating, and other maybe somehow I can take the energy out of this cloud, so that's cooling. So the net cooling is given by this this thing here, this term here, and this is the conduction term. So the K is nothing but the conduction coefficient. So this is the conduction term, which basically tells you if one part of your cloud is cooler than the other part, the energy will flow from the hotter part to the lower part. And then I have the ideal gas law. So R is the ideal gas constant by the mass of individual atoms or molecules. Rho is the density, T is the temperature, P is the pressure. So this is essentially PV equals nRT. And then what do? Well, first you figure out what is that you are talking about as equilibrium. As equilibrium, you're talking about some rho equals rho 0, T equals T0, V equals 0 as we had before. And when I say equilibrium, there should be no net heating or cooling, which means that this term is also 0. And you see that this term depends on these two thermodynamic parameters, which is the density and the temperature. And once you have got the steady state solution of these equations, what is the next thing that you do? You look at perturbation on it. And that is exactly the way we were doing last time. They have written, they said that all the perturbations will have this form. It will have a time dependent part and it will have a K dependent part. And in this case, you are looking at the stability. And so they have kept this n as a real number here. So this is what we are talking about last time when we were writing things. This was I omega. So n, what they have written here is essentially our I omega, and omega square greater than 0 tells you stability, omega square less than 0 tells you instability. So here n square lesser than 0 tells you stability, etc. Now, it turns out this analysis is very complicated. Once you put this back into here, you get a sixth order equation. And it turns out it's extremely complicated to study the stability of that. But at the end of the day, people would have found out how to look at the stability in a more pictorial form. And that's what we will see at the end of this lecture. But before we go there, we need to understand what is this term. So what are the net heating? What are the heating and the cooling elements? And again, this is a very vast chapter. I will just give you a brief overview of what are the heating and the cooling elements. Well, for the heating elements, you have the cosmic rays, which are very high energetic particles, comes from maybe outside the cloud, goes inside the cloud, and they're high energetic, so they will do collisions with the gas inside the cloud. And doing collision with the gas means increasing the kinetic energy of the gas. So that's how it heats up the gas. Similarly, photoionization also does similar thing. Photoelectric effect, you can imagine that the excess kinetic energy of the photoelectron will add to the kinetic energy of the gas. It will heat up. Shock heating is nothing but when a supernova remnant, when a supernova happens near to your cloud, it will essentially shake your cloud, and that will give it kinetic energy, again, the cloud will heat up. So these are all the heating mechanisms. The cooling mechanisms are mostly three. So one is the collisional excitation and radiation. So what happens here is, imagine that you have several gas molecules in your disposal. And so let me, so say these are few gas molecules which are, and I'm just being lazy in drawing them properly, and they're moving around, right? So they're not steady. So this is going this way, this is going that way, this is going this way, and this is going that way, etc. Now, when the heat collide to each other, sometimes these are gas molecules, or it can be atoms also. So when they collide, sometimes they'll change the electronic structure. So the electron may go up to a little higher level, and that energy will come from the kinetic energy of this molecule. Now the electron goes at higher level, so it will not stay there for long. It will come down doing a radiation. And that radiation, if it comes out of the cloud is not opaque to that radiation, it will come out of the cloud. It's basically you are creating, uh, see, you can imagine the following. When you clap your hand, so you are creating a sound wave while you are clapping your hand, and that sound wave may actually come out of this room. And as it goes out of the room, it takes away some energy which has come from your clapping. So that will take out the energy of, so this type of collision, after the collision, the radiation, when it happens, it will take out some of this energy and the gas may cool down. Free emission is the is happens because of the scattering between this cooling mechanism happens because of the inelastic scattering between two ions, or electron and electron, or electron and ion, in which case both of them has to be free. If they're free, so then one can collide with the other and goes change their track, and in between, if it is an inelastic collision, again there can be an atomic transition associated with it, which will take away some energy. Dust collision and radiation, we have also talked about, that the dusts, they will absorb the energy of some of the stars, and then mostly the stars emitting in UV, and then they will radiate in the infrared, and that infrared radiation to which the medium in which we were looking at the gas may not be opaque, and it will come out. So these are the ways you cool the gas. These are the ways you heat the gas or the cloud that we are talking about. So once we have the heating and cooling mechanism understood, and each of these one can calculate how they will depend on the temperature and pressure, you can figure out what is the net heating and what is the net cooling. And it can come up with a plot like this. So now there is a lot of going in this plot. So let us go through this plot rather slowly. Okay. First of all, this idea was first developed in this paper. It's a very, very famous paper, sometimes called FGH paper because of the acronyms of the names. And this is a lot more modern plot made by Ulfire in 2003. So what is it plotting? So first of all, in the x-axis, it's plotting density, number density. Y-axis, it's plotting the pressure. The unit is per unit Kelvin, but don't bother about it. So it's pressure in log scale, density, number density in log scale. So this is the parameter space of the thermodynamics, pressure and the density. You ask the question, given a pressure and density, how much will be the cooling and how much will be the heating function? And remember that when we talked about the equilibrium state, we said that the net heating or net cooling will be zero. So this is the net cooling, which is zero, which also means the net heating is zero. So they have calculated that in this region, so if we take, so let us first take one of these curves. In the region above these curves, the cooling, net cooling is greater than 0, means if the gas is here, it will cool down. All the processes which does cooling will dominate here. The region below this curve is the region for heating, which means if the gas is here, gas has this temperature and this density, it will heat up. The heating processes will dominate here. Remember that in the last slide we have said that both all this heating and the cooling phenomena depends on the temperature and the pressure, or any two of the temperature, pressure, and the density. So that's what we are doing here. We are saying that we have calculated the net effect of all these, and in this region the cooling dominates above the curve. Below the curve, heating dominates. And the curve is the curve where the cooling is equals to heating. So these are the equilibrium curves. So if I am anywhere in this curve, so let us look at the solid curve for the time being. If I am anywhere in this solid curve, then I have the cooling minus heating or heating minus cooling equals 0. So it's in the equilibrium condition. Nice. So I have many such curves. Well, these things will change if I go to different galactic radius. Remember that the galaxy, the stars in the galaxy are not equally distributed amongst the entire galaxy. At the center there is a bulge, there are more stars, then you have spiral arms, and after a certain radius you don't have any stars anymore. So because of that, this still heating and cooling processes will dominate, different processes will dominate at different places. And because of that, at different radius, these curves will be different. So that is what they have shown here. There are many other parameters depending on this. These curves will be different, but let me not go into so much details in one lecture. So now what we'll do is, first let us try to understand that where is temperature here? Well, it is easy to draw the isotemperature lines, because you see, if I keep the temperature constant, the pressure is proportional to the density, which means in this line log plot, so it will just look like lines with certain slope. And that's what I have drawn here. Well, it may not be exactly looking like that. You can see that I have drawn them by hand, but it's giving you an idea that how the isotemperature lines will look at. Isotemperature line means if I move along this line, the temperature remains constant. Okay, so now, so let us consider one of these curves. And as we have said, that the interstellar medium is in pressure equilibrium. So what is happening along these curves? Well, along these curves, the medium is in equilibrium, means there is no much heating, no much cooling. The gas, if it achieves that, it is trying to stay as it is, as long as it's a stable equilibrium. But if I move along this curve, obviously the pressure, temperature, density, everything changes, right? But we have also already said that the interstellar medium is in pressure equilibrium. As we have seen those from that chart, that all the different components and those numbers, the observed numbers, almost have the same pressure, which means I may say, well, if the interstellar medium is in thermal equilibrium, it will also have constant pressure. So I've drawn a constant pressure line over here, which is dissecting this curve, which is kind of wavy curve at 3 different points. So which means that if the interstellar pressure is, so this is the line at 8.5 kiloparsec, which is the solar radius, is this much, then these are the 3 stable conditions in which the gas may lie. Sorry, these are the 3 equilibrium conditions in which the gas may lie. So the gas may have this much density, number density, and this much pressure, and the corresponding temperature you can calculate, you given this ideal gas law. Here it may have this density, this pressure, and the corresponding temperature. Here it may have this density, this pressure, again the same pressure and the corresponding temperature. You have to ask the question, that are these different phases, and you can see that there are clearly 3 phases here. Are these 3 phases all give you stable equilibrium? So how do you know that? Well, let us do one thing. We'll say, okay, the gas is in here, and somehow I move the gas, I reduce the density of the gas, bring it over there. So what happens to the gas? See, if it is a stable equilibrium, it will try to go back there. Just like last time, we are talking about that 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 exercise where we said that I have this ball and it's a stable equilibrium. If I move, I have a bowl where I have put a metal ball over here near to the bottom of the ball. And if I move the ball a little bit up over there, gravity brings it down. So it will kind of oscillate around there and come back there. So if I move it away from the equilibrium, it will come back to the equilibrium. As opposed to the case where I had a pencil, which if I move away from the equilibrium, so if I bring the pencil a little bit down, it will fall down. It will go more away from the equilibrium. So let's see if these things we can see from this picture. So what I have done here is reduce the density. So pressure has to be same, remember that's in pressure equilibrium already. So I have reduced the density of the cloud a little bit. So what happens if I reduce the density of the cloud? So number density will give you, so rho by mu is essentially the number density. So if I reduce the density, keeping the pressure fixed, the temperature has to increase. Sorry, if I reduce the density, I reduce the density keeping the pressure fixed. So it comes over here. All right, the temperature has increased, but you see it is now in a region which is above the line, which means it's in a region where cooling dominates. So though I heat up the gas a little bit, bringing it here, now the cooling processes are more effective than the heating process. So the gas will cool down. And as it will cool down, what will happen? So temperature will reduce. To keep the pressure fixed, the density has to increase. It will come back there. So the gas will, even if you disturb it this way, it will go back to there. So it's a stable equilibrium. If you bring the gas over here again, which means that you have now cooled the gas a little bit because you have increased the density, keeping the pressure fixed, you have cooled the gas a little bit, but now the area is under the curve, which means that here the heating processes will dominate, the gas will heat up, it will go back there. So this point is in equilibrium. And you can check the same idea about this point. You will see that this point is also in equilibrium, because if it moves this way, the temperature increases, but it's in cooling, so it has to go back. It moves this way, temperature decreases, but it's in heating, it has to go back. What happens here? Well, let's move the gas here again. So I have hit the gas. Because of I heat the gas to keep the pressure constant, the density has decreased, so it has come here. But now it is below the curve, so it's in the heating zone. So I have heat the gas, it's now in the heating zone, so the temperature will rise and eventually it will reach there. But once it reaches there, remember that it cannot go there anymore, because if it goes there, from there it will come back again. So this essentially is an unstable point. And this, if you can imagine that if I move up this curve up and down, the stability region will be this entire portion of the curve where the curve has a positive slope. The negative slope region will be unstable, and again the positive slope region will be the stable equilibrium. So I realize that the gas in this case, mostly we are talking about the neutral hydrogen gas, is in has three phases, two stable phases, one unstable phases. And if you look at those now, the isotemperature lines now, so these are the isotemperature lines going through the border of the stable phases. Here the temperature has to be lower, obviously the density is higher, the temperature has to be lower for the same pressure. And this has lower temperature region, 100 to 1000 Kelvin. This is what we call the cold neutral medium. And this is another phase which we call the warm neutral medium. So it's interesting that in the same region of space, gas phases with different temperatures can coexist in this case. So that's the two-phase model of the interstellar medium. And it's a very interesting model. And this we say it is the unstable phase. So people expected that if you actually do an observation, you will not find much gas over here. You'll find most of the gases there. Now, initially, when people did observations, they found most of the H1 gases in the warm neutral medium or the cold neutral medium. But then when the people did careful observations, they still found gases here. And they found more gases than you expect here. And what can be the reason? So then people evoked the idea that there can be some mechanism which is creating more gases in the unstable region continuously. Well, this is not very well understood today, but I just give you a seat to think about it more and leave it there. Let me tell you a more recent picture. Recent is in 1977 of the interstellar medium, where Field, Goldstein, and Howing, the observation was more carefully looked at and redone by Mackey and Ostraker, and they have given this picture of the interstellar medium. Well, at this stage, I'll just give you the picture and leave it there. If you wish, you can again try to read this paper, which is very complicated, and we will not be able to talk much about the mathematics of this paper. Anyway, so what is their picture? So they said that it's not a two-phase medium, it's rather a three-phase medium. So you have these interstellar clouds, and like the cloud I shown you before, I did not tell you where is the warm neutral medium, where is the cold neutral medium. Mackey and Ostraker gives a very nice picture of that. They said that the core of the cloud, there is cold neutral medium, and these are the characteristic numbers for the cold neutral medium. Surrounding the cold neutral medium, you have the warm neutral medium. And you can see that these are their characteristics numbers again. So 80 Kelvin, 8,000 Kelvin. And then after that, you still have a hydrogen medium, which is warm and ionized. So it's a warm means that the temperature is not much high, so it's almost similar. The density is also almost similar, but they're ionized already. And outside that, you have hot ionized medium. Hot means that the temperature is very high now. So it's 10 to the 5 compared to 10 to the 4 over here. And the density is much smaller. So this is essentially a cloud. It's over density. That's why we call a cloud. It's 0.37 atoms per centimeter cube, very low density. But for interstellar medium, it's very high density. Here you can see it's one atom in around 1,000 or maybe 3,500, whatever, 3,000. One atom in 3,000 cubic centimeter. So this is almost rarefied. So this is kind of denser. And you have many such clouds. So this is a picture of many such clouds now going around. Some of them has a little denser core. Some of them does not have a CNM core and all. And what is happening is, so these clouds are there, and then there is a supernova which has happened nearby, and the shock of the supernova is coming through it. It's a very energetic object, and the supernova will essentially kill the outer shell. So the warm ionized medium will be gone. So you can see that it's swiping through it, and the clouds are D-shaped, and when the warm neutral medium is also reduced in size. So, but the cores may still survive. So that's what happens when a supernova passes through. And this is a kind of 20 times bigger than that picture. So these are all cartoons, as you can see. And it shows many such supernovas going around. And what happens is at the, so when these two supernova shocks are meeting, so there is a lot of compression because you're pushing the gas outside from here, pushing the gas outside from here. You have more compression here in these regions. And those compressions start to make new clouds. So the clouds are kind of extinguished here, but being made in between the supernova shells. And this process goes on. Okay, so that's it for today. So we learned about a little bit about the constituents of the interstellar medium. And we also learned about the thermodynamics of the interstellar medium and the process of formation of clouds and all in very vague picture. And that's what we can do in one lecture. In the next lecture, it will be a little bit more interesting because I will show you how to do stuff from data which are available in the internet. And I will show you the observations from external galaxies in H1 and how you can figure out several properties of those galaxies using the data which is available in the internet and a very small software. Okay, that's it for today. Please post your questions and goodbye till next time. Thank you.